The purpose of this video is to give you a walkthrough on this handout about transfer functions. Okay, so hopefully you are starting to digest the big picture. We have an input signal that is applied to some type of system. Usually this system is described by an ODE, but it doesn't have to be. There could be other ways that you describe the system mathematically. So you put in the input, the system acts on that input and produces an output. Okay, so one of the things we've talked about is this operation of convolution. And I know this seems like a complicated kind of integral to do. And for this class, it's not super important that you are able to do that computation. But the idea of this is important, that if you want to find the output, it's the convolution of the input signal. In this case, the input signal is generically represented by U of t. So that's one confusing thing about control theory. I like to use x of t as inputs, but often in control theory, U of t is what's used as the input, even though they don't necessarily mean the unit step function. Okay. All right. So when we look at this, all right, y of t, the output, is the convolution of the input with the impulse response. All right, so if we know the impulse response, and we can typically, we have methods of finding that, then you can calculate the output for any given input. Y of s is U of s multiplied by H of s. So it's multiplication in the S domain. Okay, and so because it's multiplication, algebraic rules hold, and you can find a transfer function H of s by taking Y of s and dividing by U of s. All right, so sometimes people use that as a system identification method to figure out what the transfer function is. We'll talk more about that as we move through the course. Okay. The handout notes that, all this is not true in the time domain. It's only true in the S domain. Okay. Remember, ODEs are in the time domain, and the Laplace transform turns ODEs into algebra. This is not true in the time domain. Okay. The handout notes that often transfer functions are given the generic symbol G of s. That's true, but H of s is also common. But you can use any letter, any kind of symbol to denote a transfer function. Okay, so next, remember this Laplace transform property. If I take a look at dx of t, let me go ahead and make this permanent. Okay, dx dt. If I take the Laplace transform of that, that gives me s times x of s. Okay, so when you have higher order derivatives that show up in differential equations, we've talked about this some already, then what that turns into is that you have a ratio of polynomials, one polynomial over another polynomial. Okay, and one of the things we know about polynomials is that polynomials with real coefficients have roots with certain patterns. Okay, so the roots would either be real or complex conjugate paired. All right, that's assuming real coefficients for the ODE, which is what you get in real world situations. Okay, so I like to think of this as here's this ratio of polynomials, and because it's a ratio of polynomials, I can find the roots of the top, and that would give me the zeros, and then the roots of the bottom would give me the poles. All right, so from there, we start to look at zeros and poles because we can start to imagine what they would give us in the time domain. Okay, so that's what this first example is about. And this is an important type of calculation that I expect you to be able to do when we have an exam. Okay, so you start with a differential equation, and you're assuming that the system is initially at rest. Okay, so that makes it a little bit easier. All right, and we apply Laplace transform theory. So that's what I talked about. When you hit this derivative, you get an s y of s minus the initial condition. The initial condition in this case is 0. So this becomes just y of s times s. All right, then we have plus 5y of s is equal to u of s. Okay, remember that's the input. All right, and so I can find the transfer function by taking output over input, and I get this result. Okay, so I could find the impulse response of this. Okay, then if you put u of t equal to delta of t, then the u of s is equal to 1. Y of s is u of s times g of s. You get this as the Laplace transform. You do the inverse transform, and you get this time domain result. Okay, so you should be able to do a calculation like that, and hopefully in your mind, in my mind, I think of, okay, if I apply a unit step function, an impulse function, this is going to give me this type of response. Okay. All right. So in this particular case, you could plot the pole zero diagram. Okay. And so if I put this into the form like we had before, all right, we have some gain constant K, then we have a product of zeros divided by a product of poles. Okay. So if I did some pattern matching here, all right, so I'm looking for patterns. What would the K value be? Well, the constant up front here is 1, so K is equal to 1. Okay. There are no powers of S in the numerator, so there's no no finite zeros that exist for this transfer function. When I say finite zeros, if you let S go to infinity, it zeroes out the transfer function. So sometimes people will say it has a 0 at infinity. All right, but we're only talking about specific finite numbers here. Okay, so let me clear this. Next, we have a first order pole, right? It's s plus 5 to the 1 to the first power. Okay, so n is equal to 1, and the pole is at minus 5. All right. So I could do a pole zero diagram, and so I'm noticing here that the pole is located right here. We put an X to represent poles. All right, so I have a pole at minus 5, and there are no zeros. Okay. I can envision, hopefully I can envision this impulse response based on this pole zero pattern. Okay, you start to do enough examples of these, you can kind of pick up what the output of the impulse response and the time domain would look like. Okay, so the point, remember, is now that we have the impulse response, we can handle any other type of input to the system. So in this next example, we apply 3 us of t, where us is the unit step function, and it's got a height of 3, a step up of 3. Okay, so Laplace transform theory says u of s would be 3 over s. Y of s is just u of s times g of s. G of s is this. U of s is this. Okay, so we have our transfer function. Our Laplace transform of the output. And with a partial fraction expansion, you can get this to look like this form, which lets you identify y of t. All right, and so I could, get an idea of what's going to happen. If you let t equal 0, then that starts at 0. 1 minus e to the minus 5 times 0 is 0. Okay, and so this would, let me change the pen. You can envision, without actually plotting this, you can envision that it's going to start here, and it's going to end at 3/5, y 3/5. As you let t go to 0, t go to infinity, this goes to 0. All right, and so you get an exponential response that looks something like that. Okay. All right, in the next example, we put in a ramp function. Okay, so 3t is a ramp function. When you take the Laplace transform, it's 3 over s squared. That gives you a different partial fraction, a different transfer. I'll get it right eventually. This gives you a different Laplace transform. It's got an s squared in it. And so you have to take all the lower powers of s as well. So we have something over s squared, something over s, and something over s plus 5. So that's the form of the partial fraction expansion. All right, so that's the thing I'm after here. I want you to understand the form of it. And then we can use MATLAB to actually find the coefficients. All right, and so I could take a look at this and I would get an idea that this is an equation of a line. And as t gets large, this part goes to 0 and the equation of the line dominates. All right, so here's the two things that were plotted. We could sort of visualize that without actually doing the plot. I knew this was eventually going to tend to a line by the same argument. Okay, so next, why do we use transfer functions? Well, it turns out it simplifies things. All right, we also will later see that it gives us insights into system behavior, especially when we start looking at pole zero patterns. Okay, and then we're going to also do some block diagram work where you can see where you can interface systems together and get the overall behavior. So multiple systems connect together, and this is easy to model when you have linear time invariant systems modeled by transfer functions. Okay, so this is showing this in the next example. So let's say we had two systems. R of t connects to through system 1 to Q of t. And then you take Q of t and you put it through a different system. Okay, so we have two different differential equations that relate Q of t. All right, so I see here what you can do is you can find system 1 and go through all the steps and get the transfer function. In system 2, you can take the same approach, go through all the steps of applying Laplace transforms to the ODE and get a second transfer function. Okay, then what I know is that these two systems connect, and because they have connected in series, you know, the algebra works out that you just multiply together G1 and G2 to get the overall transfer function. Okay, so here's the overall transfer function. So you can see that's much, you know, simplified rather than considering two separate systems. Okay. Again, we could then apply Laplace transform theory to get outputs for something like a ramp. I'm sorry, R of t. Remember, R of t in this case is the input. All right. So we're getting the step response, all right, to this system. All right. We find R of s is 1 over s. We take 1 over s and we multiply it by the transfer function and do the inverse Laplace transform. Okay. So I urge you to go ahead and check this in MATLAB. Let's plug this in, do the inverse Laplace transform, and you see you get this type of response. Also, would like you to be able to take a look at this type of signal and understand what it looks like. You imagine it in your mind. Okay, so I'm thinking here, this exponential is going to infinity. I'm sorry, t is going to infinity. This exponential is vanishing to 0. All right, so I'm left with just the sine component. All right, and in fact, when I graph that accurately, you get this transient response in here, but then steady states out to a sinusoid with a DC offset. Okay. All right, so if we look at the pole zero pattern here, you see a couple of things, especially with the poles. All right, so we have a couple of poles that lie right on the j omega axis. All right, and because of that, we're expecting sort of an oscillating type of response in this particular system. Okay. All right, again, you can start to, you need skills to identify important components of a transfer function. Okay, so in this case, if I asked you for the order of the numerator, all right, the numerator is 2s squared plus 1s plus 4, you can find the roots. That would give you the zeros. This would be a second order. There should be 2 zeros because it's a second order polynomial. This one, there should be 3 poles because it's a third order polynomial. All right, and you have the pole locations that you can find by taking the roots. Okay. If you factor this into the correct form, you see that k is equal to 2. We know that the order of the numerator is 2. We have the zeros. The order of the denominator is 3. We have the poles. So in summary, in this walkthrough of this document that has a discussion of transfer functions and examples, some of the things that you should be able to do, and hopefully you're starting to be able to do these pretty quickly, is to convert between an ordinary differential equation and a transfer function. That's one of the things we covered. A second thing that we covered was if you have a transfer function, you take the roots of the numerator to get the zeros. You take the roots of the denominator to get the poles. And from there, you can come up with a pole zero diagram. Okay. And one of the next steps, and we didn't cover this part of that document. I'm going to do that in a subsequent video. One of the next steps is to take a look at pole zero diagrams. And from that, visualize what happens with the time domain output. All right. You won't have to do a partial fraction expansion to do this. We'll talk about how you can get some intuition by looking at the pole zero diagram about what the response should look like. All right, so we didn't do that too much in this video, but I wanted to let you know that's where we're heading. The other thing that we did was we took a look at how you can use a transfer function approach to handle cascaded systems. All right, so in this case, we did one system connecting to another in a series type of fashion. You can have other kinds of connections, and we'll talk about those in other videos as well.